Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Today, we're diving into DNS for platform engineering and why this 40-year-old protocol remains the silent killer of production systems. October 19th, 2025, 11:48 p.m., AWS US East 1 goes down. 15 hours later, services are still failing.
And the root cause? A DNS automation race condition. Two DNS enactors in DynamoDB's management system racing each other. One deletes all the IP addresses for the regional endpoint.
It's always DNS, right? Except it's not funny when you're explaining downtime to the CEO. DNS is supposed to be simple. UDP, 512-byte limit, hierarchical lookups. So why does it keep taking down billion-dollar infrastructure?
Because we've layered so much complexity on top of that simple protocol. CoreDNS for service discovery, external DNS for automation, GSLB for traffic management, service meshes. Each layer adds sophistication, but also new failure modes.
And Kubernetes defaults that amplify your DNS queries by 5 times without you realizing it?
Yeah, the ndots 5 trap. We'll get into that.
We're going to investigate how DNS actually works under the hood, not just the phone book analogy, discover why modern platforms create new DNS failure modes, and give you the defensive playbook. Because DNS isn't just address resolution anymore, it's the nervous system of cloud-native platforms.
Service discovery, multi-region failover, CDN routing. When DNS fails, everything fails. But the ways it fails have evolved with our platforms, and most engineers don't understand the complete flow.
So let's start with how DNS really works in modern platforms. Not the textbook version, the production reality.
Right. So a query starts in your pod. You make a request to say api.stripe.com. That goes to CoreDNS, which is your cluster DNS. CoreDNS is plugin-based. It's not a traditional DNS server with zone files. It's a chain of plugins.
Wait, plugin chain? Like middleware?
Exactly. You've got middleware plugins that manipulate the request, error handling, metrics, caching, and backend plugins that provide the actual DNS data. The Kubernetes plugin watches the API server for services and endpoints, generates DNS responses on the fly for anything ending in cluster.local. It's dynamic, which is perfect for ephemeral pods.
But that means if you're querying an external domain, CoreDNS forwards it upstream?
Yep, the forward plugin handles that. Sends it to your upstream recursive resolver. Could be 8888, your corporate resolver, whatever you've configured. From there, it's the traditional DNS hierarchy. Recursive resolver queries root servers, TLD servers, authoritative servers, caches the response with a TTL, and returns it back down the chain.
And each of those layers is caching with different TTLs.
Exactly. Which is where things get interesting, because you don't control every resolver's behavior, but before we get to that, there's the external DNS piece.
Which automates DNS record management for your ingresses and services.
Right. External DNS is a controller that watches Kubernetes resources and synchronizes DNS records with cloud providers, Route 53, Cloud DNS, Azure DNS, 50-plus providers via webhooks. Super useful for automating DNS, but it's also where you get automation race conditions like the AWS outage.
Okay, so we've got this elegant, simple protocol underneath, but we've stacked CoreDNS plugins, external DNS automation, service mesh discovery, GSLB health checks on top. Where does it break?
Let's talk about the ndots 5 trap, because this one bites everyone.
I'm guessing this is a Kubernetes default that seemed like a good idea at the time.
Legacy compatibility with search domains. Kubernetes sets ndots 5 in etcresolve.conf. The ndots parameter controls how many dots must appear in a name before DNS tries it as an absolute query. If your query has fewer than 5 dots, Kubernetes tries all of the search domains first.
So if I'm querying api.stripe.com, that's only 2 dots?
Right. So with ndots 5, Kubernetes first tries api.stripe.com.default.svc.cluster.local, then api.stripe.com.svc.cluster.local, then api.stripe.com.cluster.local, then api.stripe.com as a root query, and finally as an absolute query. That's 5 DNS queries for one external domain.
5 queries, 4 of them failing with NX domain.
Exactly. 5 times amplification on every external API call. I've seen production cases where a high-throughput service went from 500 milliseconds latency to 50 milliseconds just by fixing ndots.
So what's the fix?
Lower ndots to 1 in your pod's DNS config, or use fully qualified domain names with a trailing dot, which bypasses the search list entirely. And for high-throughput services, implement application-level DNS caching.
This feels like one of those defaults where the cost is invisible until you're at scale.
That's the pattern with DNS. The complexity is hidden until it cascades. Let's talk about TTL balancing because there's no perfect answer here.
Low TTL for fast failover, high TTL for performance, classic trade-off.
Yeah, but the stakes are different depending on your service. If you're load balancing backends that change frequently, you want low TTL, 60 to 300 seconds, so failover is fast, but that increases query load on your DNS servers and upstream resolvers.
And high TTL, like 30 minutes to a day, gives you better performance and reduces load, but delays failover.
Right, and here's the catch. You don't control the DNS caching hierarchy. Some internet service providers ignore your TTL hints. You can set TTL to 60 seconds, but if a resolver decides to cache for 5 minutes, you're stuck waiting.
So your failover SLO is only as good as the worst resolver in the chain.
Exactly. Now let me throw another wrench in, Anycast routing. Everyone thinks Anycast routes to the nearest node for lowest latency.
It doesn't?
Not necessarily. BGP routing uses AS path length and policy, not geographic proximity. Studies show many queries travel to Anycast sites much farther than the closest, inflating latency due to propagation delay. If you've got strict performance requirements, you need to configure Anycast prefix advertisements carefully.
So nearest in BGP terms isn't nearest in latency terms.
Right. And then there's GSLB, Global Server Load Balancing. GSLB manipulates DNS responses based on health checks and geography. Sounds great until you realize that if a health check fails and GSLB returns new IPs, those are subject to TTL caching. 300-second TTL means 5 minutes before all resolvers see the failover.
So your failover SLO is only as good as the worst resolver in the chain? And cached negative responses can persist even longer.
Yep. So all these layers, CoreDNS plugins, external DNS automation, service mesh discovery, GSLB health checks, they add sophistication, but they also add new failure modes. And when you look at the outage postmortems, that's exactly the pattern.
Okay, let's talk about the AWS outage because that's a masterclass in how DNS automation can cascade globally.
October 19th to 20th, 2025. DynamoDB's DNS management system has 2 components for availability. A DNS planner that monitors load balancer health and creates DNS plans, and a DNS enactor that applies changes via Route 53.
Separation of concerns. Planner decides what to do, enactor executes it.
Right. But here's where the race condition happens. You've got multiple DNS enactors for redundancy. One enactor is slow, working through an old DNS plan. Meanwhile, the planner keeps running, generating newer plans. Another enactor picks up a newer plan and rapidly progresses through all the endpoints.
So the fast enactor finishes while the slow one is still applying the old plan.
Exactly. Fast enactor completes, invokes the cleanup process to delete old plans. But at the same time, the slow enactor applies its old plan to the regional DynamoDB endpoint, overwriting the newer plan. Then cleanup runs, sees this plan as many generations old, deletes it. All IP addresses for the regional endpoint gone. Empty DNS record.
15 hours of cascading failures because 2 automation processes raced and cleanup one.
Yeah. DynamoDB goes down, takes all dependent AWS services with it. Customer traffic, internal AWS services that rely on DynamoDB, Slack, Atlassian, Snapchat, all downstream. AWS disabled the DNS planner and enactor automation globally.
What's the lesson there? Don't automate DNS changes?
No, the lesson is DNS automation needs coordination locks, generation tracking, and safeguards against empty records. Race conditions in DNS cascade globally because DNS is the foundation. You can't treat DNS changes like normal automation.
And it's not just AWS. Salesforce, in May 2025, engineers' quick fix to DNS configuration, bypassed review, cascaded across infrastructure.
Right. There's no such thing as a quick DNS fix. DNS changes require thorough testing, staged rollouts, automated rollback. And then AdGuard, in September 2025, traffic rerouting redirected Asian users to Frankfurt. Frankfurt capacity couldn't handle the 3 times load spike.
So capacity planning has to model failover scenarios, not just normal traffic patterns.
Exactly. These outages reveal the same pattern. Simple protocol, complex systems, brittle automation. DNS failures aren't usually protocol issues. They're automation bugs, capacity planning gaps, configuration errors. Understanding how all the pieces fit together is your only defense.
Okay, so what's the defensive playbook? Because I'm assuming there's more to it than just be careful with DNS.
Yeah, it's a 5-layer defense. Optimization to reduce query volume, failover for multi-region resilience, security to prevent hijacking, monitoring for visibility, and testing to simulate failures before production.
Let's start with optimization because I want to fix that ndots 5 trap.
First, lower ndots to 1 in your pod specs. Add DNS config with ndots 1 eliminates 4 times amplification for external domains. Second, use FQDNs with trailing dots, api.example.com dot, bypasses the search list entirely, drops you from 5 queries to 1.
What about CoreDNS itself?
Tune the CoreDNS cache. Increase cache size to 10,000 records, TTL to 30 seconds. In your core file, that's cache 30 with success 10,000. And for high-throughput services, implement application-level caching. Cache DNS results with TTL respect. Don't hammer CoreDNS on every request.
Latency benchmarks, what should we be aiming for?
Under 20 milliseconds is excellent. That's local. 20 to 50 milliseconds is solid for cloud. 50 to 100 is acceptable. But once you're over 100 milliseconds, you're degrading application performance. That's your warning threshold. 300 plus is critical.
Okay, failover. How do we design multi-region resilience?
GSLB with health checks. Use Route 53 or equivalent, health checks monitoring your endpoints every 30 seconds, failover routing policy with primary and secondary regions. For active-active, use latency-based routing.
And TTL strategy?
60 to 300 seconds for load balance backends, fast failover. 3,600 to 86,400 seconds for stable infrastructure. You're balancing failover speed against query load.
Multi-provider strategy?
Don't rely on a single DNS provider. Use NS records with multiple providers, Route 53 plus Cloudflare. Client-side resolver fallback, 8888 plus 1111. And combine Route 53 health checks with CloudWatch alarms, so you can fail over based on application metrics, not just ping.
What about security? Because we haven't talked about DNS hijacking.
3 pieces: DNSSEC for integrity, DOH or DOT for confidentiality, and enterprise control over resolvers. DNSSEC validates authenticity of responses, prevents cache poisoning, and man-in-the-middle, but it doesn't encrypt traffic.
That's where DOH and DOT come in.
Right. DNS over HTTPS uses port 443, blends with HTTPS traffic. DNS over TLS uses port 853, visible but encrypted. Mozilla's 2024 study showed 90% reduction in third-party tracking with DOH.
But enterprises lose visibility.
Exactly. NSA's recommendation: Use DOH with internal enterprise resolvers, not public 111. Block external DNS queries on ports 53 and 853. Validate DNSSEC. That maintains security visibility while encrypting queries. It's DNSSEC for integrity plus DOH for confidentiality, not either or.
Okay, monitoring. What metrics actually matter?
Query latency first. Track P50, P95, P99. Alert if P95 exceeds 100 milliseconds for warning, 300 for critical. Breakdown by query type, A, Quad A, SRV, and destination, internal versus external.
Error rates?
Yep. Monitor NX domain, serve fail, refused, timeouts. Spike in NX domain might indicate misconfigured apps. Serve fail indicates upstream issues. Also track top requesters. Identify pods generating high DNS volume. Could be missing application-level caching or runaway retry loops.
And upstream health?
Monitor CoreDNS to upstream resolver latency and error rates. Detects if your upstream, 8888 corporate resolver, is slow or failing. Tools like Datadog DNS monitoring, Prometheus CoreDNS metrics, custom exporters for external DNS sync lag.
Last piece, testing. How do we simulate DNS failures before they hit production?
DNS failure game days. Kill CoreDNS pods, block port 53, inject latency with chaos engineering tools. Observe saturation on queues, thread pools, application behavior. Does your app degrade gracefully or crash hard?
Capacity modeling.
Load test your DNS resolvers with realistic query patterns. Model failover scenarios. What if Asian traffic routes to Europe? That's the AdGuard lesson. And test DNS changes in staging with the same query load as production. Automate rollback if error rate spikes.
Client resilience?
Applications should retry DNS queries with exponential backoff, fall back to cached IPs, degrade gracefully when DNS is unavailable, because no matter how well you've designed your DNS infrastructure, it will fail at some point.
So, to recap, the defensive playbook. Optimize to reduce query volume, fix ndots, use FQDNs, tune caching, design multi-region failover with GSLB and balanced TTLs, secure with DNSSEC plus DOH using internal resolvers, monitor latency and error rates with meaningful thresholds, test failures before production with game days,
And understand that DNS isn't simple anymore. You've got CoreDNS plugin chains, external DNS automation, service mesh discovery, GSLB health checks. It's complex distributed systems engineering. The only defense is understanding how all the pieces fit together.
Because when DNS fails, it's not just the internet is down, it's DynamoDB cascading to Slack and Atlassian. It's 500 millisecond latency because of ndots 5. It's traffic rerouting overwhelming your data center capacity.
Right. And it's always DNS stops being a joke when you've got the playbook. You can debug production latency issues, design resilient failover, optimize for your workload, monitor the right metrics, simulate failures before they happen.
The simple protocol isn't simple anymore, but you're ready for it.
Exactly. DNS is the nervous system of cloud-native platforms. When you understand how it works, really works, not just the phone book analogy, you can prevent your platform from becoming the next postmortem.
That's the defensive playbook. Optimize, failover, secure, monitor, test, and understand that every layer of abstraction adds new failure modes.
The AWS outage, the Salesforce disruption, the AdGuard capacity failure, they all had one thing in common: DNS automation without the defensive playbook. Now you've got the playbook.
Don't just assume DNS works. Understand why it's the silent killer and tame it.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening. and see you next time inside the Platform Engineering Playbook.